Hello students, welcome back. Previously we studied some elementary exponential equations, those with integer coefficients like this or that. And something like this is going to be a bit harder because of the denominator, but still we have only integer coefficients, so we can use pretty much the same technique. Regard those as a quadratic equation of e to the x, solve it using factorization technique or whatever, and then in the end, take the natural log to replace the x value in place of e to the x. Please remember the possible extraneous solutions and you're going to be fine. Now let's go over to a little bit harder examples, those down here, and we need some bigger font here. Even bigger. First we have e to the negative 3t, negative 0.3t, and down here e to the negative 0.4t, and even more decimals flying around. So these problems are fundamentally different from the previous problem with integer coefficients only. Now, how do we get all those decimals flying around? That's because these are associated to real-life modeling problems. We call those logistic equations. Logistic models and equations. Now, before going over to the technicals of problems D and E, let's have just a little of digression on logistic models. It won't be too long, about 4 or 5 minutes. Let's copy and paste this function here in the left-hand side from the first equation, and let's plot it from negative 10 to 10. Let's start from there. Okay, that's the graph. What do you see? An exponential growth? Yeah, it looks like it. What if I go a little bit further to 20? Looks like the growth is slowing down. What if I go a little bit further to about 30? Now you can see the full picture. Not just slowing down, but also stabilizing, pretty close to 500. And then we have 500 up there. Is that a coincidence? Probably not. There's no such thing in mathematics. If t gets really, really large, kind of like infinity, then e to the negative 0.3 times infinity. So this is basically e to the negative infinity. That's 0. So 25 times 0, so this whole thing is 0, so adding 0 changes nothing, and we end up with 500 over 1, roughly speaking, or pretty close to it. Indeed, I can couple these and show you these behaviors. So we have a horizontal asymptote. That's a stabilizing value. This kind of models are extremely useful in real-life situation. The applications of these are abundant. For example, how about some population dynamics? In a certain closed environment, say for example, in your lab you're growing bacteria, kind of like this. Very little and slow growth, and you have an explosion, and then later slowing down and stabilization. What if you introduce some foreign species, such as a herd of deer, to an island, which is basically a closed environment? We have something like this: slow growth, explosion, and stabilization. Disease spreading around through community and eventually reaching the mature population of infected people. Rumors spreading out on social media, effect of marketing or announcements reaching some maximum capacity, and so on and so forth. There's so many applications, not just in natural science such as biology or epidemiology or public health, but also in behavioral sciences such as social science, political science, business and marketing, etc., etc., etc. This is an extremely important type of modeling, and that's what we're going to study here and also here. Okay, so much for the digression. Now let's go to the technicals. How do you solve this equation? Well, this is basically a modeling problem, or at least I'll regard it as a modeling problem. So let me change the equation kind of like this to approximate equality. Okay, let's go from there. And then what do you do? Well, we have basically a linear equation of this exponential, which I'm highlighting in red. So let's solve it. And then in the end, we're going to take the log to find out t. So how do you find out e to the whatever power? Through typical method of linear equation. Remember this three-step process, which I said in day 1, I'll probably end up repeating 100 times. What is step 1? Denominators, that's step 1. Step 2, parentheses. Step 3, like terms. Do you remember those? And then after finding out what exponential is, we have to get t, so we have step 4. We have to take the inverse, in this case, logarithm. That's a strategy. So I wasn't kidding when I was emphasizing this in the day 1, the very first day, and I may end up repeating this 100 times. Yes, indeed, it's that important. Okay, let's go. Let's start from here, and then let's remove the denominator. How do I do that? Multiply the same denominator, 1 plus 25 e to the negative 0.3t, this one, to both left-hand side and right-hand side. Multiply the same thing to both left-hand side and right-hand side, will not change anything. And then in the end, what do we get? This denominator and this thing up here would cancel each other out. So divide these out, divide that out, and we have just 500 on the left-hand side. And the right-hand side, we have this. And then we'll have to break up the parentheses in step 2, but I cannot resist this, so let's take just one more step. Divide by 100 from both left-hand side and right-hand side to simplify. Normally, just breaking out the parentheses is what you do, but in this case, some simplification was a little bit easier, so we did it that way. This step is not really necessary, but in this case, it really helps us. Okay, now let's go to step 2, parentheses. How do you break up a parentheses? Basically, we need this. Distribute 2. So 2 times 1 is 2. 2 times 25 is 50. Remember all those? So multiply by 2 and multiply by 2. There you go. We have only one parenthesis to break up, so it was done rather easily in a single step. Okay, now let's take the like terms together. Let's start from here. And we have to move this one away, so subtract 2 from both left-hand side and right-hand side. 2 minus 2, that's 0, so that's going to be gone. And here I'm going to get 5 minus 2, that's 3. Okay, all right. And then let's go ahead and solve for exponential. I can divide by 50, so 3 over 50 is approximately equal to this exponential. Consequently, this exponential is equal to, what is 3 over 50? 6 over 100, so 0.06. You can check with your calculator. Okay, we're almost done here. We got exponential expression here. So all you have to take is the inverse. Take the log of both left-hand side and right-hand side. Oops. Typo, sorry about that. And then log and exponential, of course, will cancel each other out. That was the point for all this. Basically, it's this cancellation that we want. And that's why we took this cancellation, or this inverse function natural log, to begin with, to kill off this exponential. So in the end, what do you get? Negative 0.3t is log of 0.06. So therefore, t is approximately equal to log of 0. Divided by negative 0.3. Sorry about that. Sorry about my mouse work mistake. In the end, what do you get? Log of 9.37 something. About 9.4. For example, if this modeling had been, say for example, introducing some herd of deer into an island, and then how long will it take for this deer population to reach 200, for example? According to this modeling, about 9.4 years, or something like that. Here's a problem, logistic model problem. The stabilizing population over 1 plus some coefficient times exponential of negative something t, that's the situation. Step 1, remove the denominators by multiplying this denominator both left-hand side and right-hand side. And then break up the parentheses. In this particular case, I did some simplification beforehand. And then break up the parentheses. Take the like terms together, flip this 2 to the other side, and then you can go ahead and solve for e to this one, negative 0.3t. And then you have all those computations done. Okay, we have exponential. Go ahead and take natural logarithm, and then punch it to calculator. That's how you do it. That's the standard process. Now, do you have enough time for another exercise like this? Not really, so let's stop here. And we're going to come back and do the same problem, or more precisely speaking, same type of problem in part E. But when you do it for the second time, let's do it a little bit more quickly. See you soon.